I welcome you all for this NPTEL online course on earthquake geotechnical engineering, and we are discussing a very important topic of this course, that is on liquefaction of soils. We are working on the module 4 of this course. The module 4 is on liquefaction, and we already covered 2 chapters on this module. One is introduction and liquefaction susceptibility. So, we have covered so far 5 lectures, and today is the 6th lecture of this module, and we are going to start from that is the 3rd chapter, that is the initiation of liquefaction. What we are going to cover in this chapter, that is the 3rd chapter of this, which is 2 topics has been already covered: flow liquefaction surface and inflation of excess pore pressure. Today we are going to talk the 3rd topic, that is evaluation of initiation of liquefaction, which can be understand by using 2 approaches. One is called cyclic stress approach and another is cyclic strain approach. So, one of them, that is cyclic stress approach, we will discuss in very much detail, and in this approach what is required to be done, that we need to characterize the earthquake loading as well as liquefaction resistance by the same terms, whether whatever we decide accordingly we will characterize earthquake loading as well as liquefaction resistance. And in fact, it is mostly in the cyclic stress approach, it is in terms of cyclic shear stresses, both are characterized. Now, coming to the characterization of earthquake loading, it is done by 2 processes, either simplified procedure or what we call the ground response analysis. Similarly, characterization of liquefaction resistance is done based on the laboratory or institute test. So, we will discuss the first one, characterization of earthquake loading, today completely, and characterization of liquefaction resistance will be discussed partially. So, coming to this today's lectures, we are going to talk about cyclic stress approach after the introduction, and then characterization of earthquake loading and characterization of liquefaction resistance will be done, and that will be based on the laboratory test only, because we will not be able to carry this lecture on the institute test. We will continue in the next lecture for that. Now, coming to this most of the stuff from this lecture number 36 is from the reference by Geotechnical Earthquake Engineering by Kramer. You know that we already discussed that steady state and flow liquefaction surface. So, we discussed 2 things in the last 2 lectures. One was flow liquefaction surface, FLS in short, and another was steady state line, SSL. So, using these 2 concepts, provide a complete framework for basic mechanism of liquefaction can be understood by this framework. This framework will integrate different steps of liquefaction, which is 3 steps. One is the liquefaction susceptibility, liquefaction initiation, and the liquefaction effects. So, all 3 will be integrated together. This will illustrate today we are the important influence of excess pore pressure generation on the extent of liquefaction related hazards. So, how when the pore water pressure generates, so how it influences the liquefaction, that we are going to discuss in detail. As we discussed that there are 2 approaches, one is cyclic stress approach, we will call it in short CSA, and another is cyclic strain approach, we will call it CSNA there. So, we will discuss in the next 3 lectures, including this one, another 2 lectures, cyclic stress approach only. Coming to CSA, cyclic stress approach, when we talk about many advances in the state of knowledge of liquefaction is concerned, I think if you recall when I started this topic on liquefaction, then we discussed 2 major earthquake of the world, after which liquefaction started worldwide. So, one was in Japan, which was in Alaska in USA, one was which happened in March 1964 with magnitude 9.2, and another was in Japan, Niigata earthquake, that was also in June 1964. So, within a span of 3 months. After that, a lot of studies started, and the initial studies started from the work which is done by Harry Bolton Seed at University of California, Berkeley, and it was done mostly publications in 60s and 70s and later also. So, this research was directly largely towards evaluation of the loading conditions required to trigger liquefaction. So, idea is that what is the loading required from the earthquake which will trigger the liquefaction. So, that was the idea objective of this initial study of seeds. In that case, the loading was described in terms of what is called cyclic shear stresses, and liquefaction potential was evaluated on the basis of the amplitude and number of cycles of earthquake induced shear stress. So, what is done, that loading is represented in terms of stress, cyclic shear stress, and then for this, because as cyclic loading is applied. So, in that case, what is the amplitude of the loading and number of cycles that become important to for. So, and these amplitude and number of cycles will govern the cyclic shear stresses induced inside the soil, which will trigger ultimately the liquefaction. The first, of course, it could be there also, but very well known or established paper on the liquefaction first, which was widely used, is by Seed and Lee in 1966, which defined the initial liquefaction as a point at which the increase in excess pore pressure, that is in short we called EPP, is equal to the effective confining pressure, that is, let us say, if I say U excess, this U excess is nothing but it represents your EPP. I think we discussed in the last lecture also this thing. So, this is EPP, excess pore pressure, and if the excess pore pressure become equal to the effective confining pressure, which could be said as the minor principal stress, effective minor principal stress sigma 3c, or in the triaxial test it is also called cell pressure or confining pressure. If excess pore pressure is equal, that is the condition of for initial liquefaction. The ratio of U excess pore pressure and divided by U excess divided by sigma 3c is called nothing but this ratio of these two is called RU, which is called short in pore pressure ratio. So, another way I can say that when RU become 100%, then that is the condition for initial liquefaction. So, initial liquefaction could be produced in both loose and dense specimen, which is like that for the flow liquefaction the condition is that the sample should be loose, but cyclic mobility could occur either in the loose sample as well as dense sample. So, initial liquefaction can occur in both cases, as loose as well as in the dense sample. Only the when it will trigger, that will different for the depending on the relative density. Now, continue with the cyclic stress approach. It is conceptually very simple. And why it is simple? Because the earthquake induced loading, or we say in the in a simple word seismic loading, is expressed in terms of cyclic shear stresses, and it is compared with the liquefaction resistance of the soil. So, one side you have the cyclic shear stresses which is induced inside the soil due to the earthquake loading. On another side you have the liquefaction resistance of the soil, which is also represented in the same number, same terms, that is in terms of cyclic stresses only. And then what you could do at the locations where the loading exceeds the resistance, what will happen? Liquefaction is expected to occur. So, this is the simple. So this way, like both it is represented in terms of cyclic stresses, shear stresses, both loading as well as resistance. So, this is as simple. Continue with this one. Now, in the CSA, the next step is how we characterize of earthquake loading. So, we will discuss first characterization of earthquake loading, and once it is over, then we will discuss characterization of liquefaction resistance. So, next few slides will be on characterization of earthquake loading. The level of EPP, that is excess pore pressure required to initiate liquefaction, is related to the amplitude and duration of earthquake induced cyclic loading. So, how much pore pressure is developed inside the soil, that will depend on your loading condition. And when we talk about loading condition, this loading condition is related to the amplitude and duration of cyclic loading. The cyclic shear stress approach, CSA in short, is based on the assumption that the EPP generation is fundamentally related to the cyclic shear stresses. Hence, seismic loading is expressed in terms of cyclic shear stresses, simple. Here one side we are saying that liquefaction, who is responsible for liquefaction? It is increase in pore water pressure. So, what happens when you induce the loading inside, it will create excess pore pressure, and we are linking with the generation of cyclic shear stresses. So, the loading can be predicted, which is like due to the seismic load in terms of cyclic shear stress by using two methods. One is detailed ground response analysis, which is called GRA in short, and another is what we call using a simplified processor. Ground response analysis also has been covered in pretty much in detail during this course only, where we carried out 1D analysis and 2D ground response analysis, and so that way also it can be done. But suppose if you do not have means to carry out the ground response analysis, then we can go for simplified procedure. So, let us discuss first about GRA approach, and then we will discuss the second part, that is simplified procedure. So, as for ground response analysis, it can be used to predict time histories of what? Shear stresses. That means, the ground response analysis will give you the variation in shear stress with the time at various depth, and this will vary with the depth. It is not going to be constant, rather at different level of depth inside the soil, that this time history will be different. Such analysis produce time histories with the transient irregular characteristics of actual earthquake motions. However, so what happens when we carried out ground response analysis, you plot time history which looks like this one. Let me show you this, the time history for the coming, this kind of time history you will get, and this is what this time history. This is on y axis you have shear stress, on x axis you have like time. So, in this time history it is very irregular, but it has been observed that the data which has been obtained from the laboratory data it says you uniform time history. So, if you want to compare like liquefaction resistance, because if you want to particularly when you deal with the, you want to find the liquefaction resistance using the laboratory data, then in that case you need to have the uniform time history. That means peaks are like peak values are equal, and here peaks are not equal. So, usually obtained so what we do here, therefore, for comparison of earthquake induced loading with laboratory determined resistance require conversion of an irregular time history which has been obtained using GRA to an equivalent stress of uniform stress cycles. So, you have the peaks are going, some peaks are high, some peaks are low, but we require uniform shear stress time history. To convert, the Seed et al. In 1975 suggested a weighing procedure to a set of shear stress time histories from recording strong ground motion to determine the number of uniform stress cycles. And what was the procedure? It was conveyed, it was like after like from so many data from the field, uniform stress cycles which is like NQ means number of cycles which have an amplitude of 65% of the peak cycle shear stress, that is toe cycle, where toe cycles you can say the average cyclic shear stress is about 65% of the maximum value, that is 0.65 toe max. That will produce an increase in pore pressure equivalent to that of irregular time history. The equivalent number of uniform stress cycles will increase with increasing earthquake magnitude. So, now the number of cycles, one side first you put uniform cycles, and for uniform cycle you need to just simply the peak value is maximum value is multiplied by 0.65, that is there. But on another side, how many number of cycles need to be considered, that will depend on your magnitude of earthquake. And like from the by Seed et al. 1975, number of equivalent uniform cycles, that is N equivalent for earthquake of different magnitudes are given in this figure. So, here you have three curves in this figure. Central curve is mean curve. So, normally we will naturally will be using the middle one. So, in the middle curve if you want to read, so use for 7 magnitude earthquake, what I get? For 7 magnitude earthquake you get almost 10. If you go for 7.5, then about around 15 or 14 you get. So, for 7.5 magnitude you have this one here, this will go like this one. So, this is around less than 15, around 14. Similarly, for 8 magnitude around 20. So, roughly if you want to find magnitude and NQ, M and NQ, if I link for 7 magnitude earthquake, so you have 10 here, then you have 7.5 around 15 and 8 magnitude around 20. So, this is that can be read from here. Coming to this this characterization, like in this case, this is a typical irregular time history of shear stress and this has been by a magnitude 7 earthquake, MW7. So, naturally the number of equivalent number of cycles will be for this, as we just discussed, is 10, it will be approximately 10. And here in this case the peak value is, though it is in terms of here in pounds per square feet. So, the peak is here. If you convert this peak into equivalent kPa, then you get 37.4 kilopascal, and the toe cycle for this maximum value will be 0.65 toe max. So, you get 24.3 kilopascal. So, that means this shear stress time history, which has been generated using what we call ground response analysis GRA, will be have equivalent uniform shear stress with amplitude 24.3 kilopascal and number of cycles as a 10. So, that will be the answer here. So, this way we carried out the ground response analysis. This way we find out the equivalent number of cycles, toe cycle and the number of cycles using ground response analysis. Now, this characterization of earthquake loading can also be done using what we call the simplified procedure, and this simplified procedure is written in the short as SP. Here SP stands for simplified procedure. This simplified procedure was given by Seed and Idris in 1971. So, the uniform cyclic shear stress amplitude for level or gently sloping sides can also be estimated using the relation here. What has been said by the simplified procedure, if suppose you do not have the ground response analysis, but you know the peak value, and this peak value is peak ground horizontal acceleration, which is not related to shear stress, because shear stress we are calculating based on this. So, Amax if is known, then ratio of Amax by G will be dimensionless, multiply by sigma V. What is sigma V? Total overburden pressure in the vertical direction, and RD is a reduction factor, and this RD is the value of stress reduction factor. This is called a stress reduction factor at the depth of the interest. At the ground level, when at Z equal to 0, the value of RD is 1. So, once toe max is known, then toe cycle can be simply calculated 0.65 multiplied by toe max, that means 65% of the value of toe max. As for RD is concerned, RD can be calculated from this graph. Here you have again depth is in the feet, which is 0 to 100 meter, 100 feet is roughly 30 meter, and the value of RD is given. You see, when at ground level the value of RD is 1, and when the depth increases it decreases, and what we do if we use this chart, then we use the average values, because it is a range for different soils. So, normally if you use the average values, and then if I extend this chart, then it will be like this. So, you can extend it and then it can be used. However, in the absence of this chart, the Leo and Whiteman, this chart has been given by Seed and Idris in 1971. So, this is this chart, and Leo and Whiteman have suggested following equations, two equations. If your depth is less than 9.15 meter, then reduction factor can be found out one, where Z is the depth of the point where you want to find in terms of meter, not in feet. So, the Z in this equation is in terms of meter. So, putting the value of Z in meter, we can calculate the value of RD from this formula. Similarly, if your depth is more than 9.15 meter, however less than 23 meter, then we can use the second equation. If Z is more than 23 meter, you may not require, because mostly below 20 so much depth liquefaction may not occur. So, anyway we can use these equations, because that they are straightforward and it can be programmed also in Excel sheet or maybe like this. So, we are set, we know the Amax, we know this G's, only the thing sigma V, effective overburden pressure, and that will vary with the depth. If you know the unit weight, then sigma V is simply can be calculated. Sigma V is nothing but, for the particularly if you have total stress, sigma V is into gamma into H, where gamma is nothing but gamma into Z, where Z is the depth, gamma is unit weight of the soil. So, this way we find out. Now, continue with the simplified procedure. The uniform cyclic stress, shear stress is assumed to be applied for the equivalent number of cycles, which depends on the earthquake magnitude, which we already discussed. Regardless of whether a detailed ground response analysis or the simplified procedure is used, to characterize the earthquake loading, you have two procedures. One is ground response analysis, another is simplified procedure, which we already discussed here. The earthquake, irrespective of the procedure you use, any of the procedure, the earthquake induced loading is characterized by a level of uniform cyclic shear stress that is applied for an equivalent number of cycles, and this equivalent number of cycles depends on your earthquake magnitude. If your earthquake magnitude is higher, equivalent number of cycles will be high. If it is low, it will be low. It is like this. Now, coming to this one of the example where you can see that how we can use this what we discussed earlier in the characterization of earthquake loading using simplified procedure, because here it is difficult to deal with the ground response analysis. In this case, a site is subjected to earthquake shaking, and this earthquake shaking produces a peak ground acceleration of 0.22 g. So, simply what it is saying, your A max is 0.22 g. Plot the variation of maximum shear stress, that is tau max with the depth, and also equivalent uniform cyclic shear stress tau cycle with the depth. So, you need to plot the variation with that, and this is simple. What is happening? You have 3 layers of the soil. First layer is 3 meter top, then 2 meter and 5 meter. Water table is located at the top of the second layer, at the base of the second layer, at the top of the third layer, and the unit weight, that is dry unit weight, is varying 15-16. Here it should be not dry, because once you have the water table, so you assume that this is the kind of saturated ore. So, this is hypothetical, because this will be saturated will be the higher value, but this will not be dry because water table is here. So, coming to this data, now here using the simplified procedure of seed and ridge, the maximum shear stress can be estimated from the relation tau max equal to A max by G sigma V into RD, where tau max by G is given to you 0.22 sigma V into RD. So, using this relation we can find here what you need to use, you need to have the sigma V and RD reduction factor. So, variation of tau max with the depth requires evaluation of the variation of vertical stress and RD, which has been done in the table here. So, in this case calculation has been done, sigma V will be gamma h. Here, because in this equation you need to understand, in this equation or in the last equation which we have discussed, sigma V is total stress, a total overburden pressure, it is not effective. So, when you find the cyclic shear stresses induced inside the soil due to earthquake loading, then total overburden pressure need to be used, not the effective. This is the common mistake which is done many times. So, whenever any numerical you have, try to understand that tau max or tau cycles due to earthquake loading will be calculated based on the total. So, once you calculate total stress, then what location of water table is not going to make a difference, whether where irrespective of where, because ultimately you are not going to calculate the effective stresses. So, and the total stress is not going to be vary, total stress will be the same. So, in this case, so this is calculated, for example, at the depth 0 naturally you do not have sigma will be 0, at 3 meter level 15 into 45, the next level it is something will be added and this continue to be added. So, here I think one mistake is here, this is all right. So, we can correct it, this is 20 here basically, this value is 20 and this should be treated as gamma saturated, this is all right. So, this is misprinting here. So, this is gamma saturated 20 kilonewton per meter cube, this has been taken 20 here. If you calculate here in this table, the parameter gamma saturated is taken 20, this is all right here. So, this way you have sigma V has been calculated, and for 3 depths sigma V can be calculated. RD, as we discussed, RD will be varying with the depth, at that 0 it will be 1, 0.98, 0.97, 0.93. So, tau max can be calculated using this relation which is in kPa kilonewton per meter square and tau cycles, because sigma V is increasing with the depth. So, as a result your both tau max and tau cycle will be increasing with the depth, but only the difference that this last column tau cycle will be 65% of the tau maximum, and once you plot, then this plot will be looking like this one, that how the shear stress varies with the depth. With the depth, the basically shear stress is increasing. So, this way and this calculation should be done in the tabular form to avoid anything. So, this was one of the example on simplified procedure to calculate the shear stress induced inside the soil due to the earthquake loading. Here this looks a straight line, but it will not be straight line actually, because the reason being that because the slope might be different, because the gamma is not constant. If gamma is constant with a homogeneous soil, then you will get the straight line like this. Coming to the next part of the today's lecture, this lecture, we have done with the characterization of earthquake loading or seismic loading, and we discussed 2 methods, one is ground response analysis, another is simplified procedure. Now, how to characterize the liquefaction resistance, that is the strength of the soil, and we already said it can be characterized by 2 methods, one is laboratory, another is field test. So, the failure state for flow liquefaction is defined using the flow liquefaction surface, and its initiation is easily recognized in the field. So, recognize whether flow liquefaction is started or not, it is easy to guess, but it is difficult for cyclic mobility like where at what point cyclic mobility is starting. So, that is not a distinct point, and there is no distinct point at which cyclic mobility failure can be defined. So, as a result, what is done, some like that strain or some pore pressure is estimated. So, cyclic mobility failure is generally considered to occur when pore pressure becomes large enough to produce ground oscillations. So, that is the point where the pore pressure becomes large enough and the ground oscillations are produced, lateral spreading or other evidence of damage at the ground surface. So, the cyclic mobility have started where you have excess pore pressure, and pore pressure reached to the point where lateral spreading started or there other damage on the ground surface have started. In that case, we shall assume, rather than like in the flow liquefaction, soil started flowing, but soil may not start flowing in the case of cyclic mobility. So, characterization of liquefaction resistance is developed along two lines methods based on the results of laboratory test and methods based on the institute test, as we discussed earlier. Now, coming to the characterization which is based on the laboratory test. Most laboratory tests were performed on isotropically consolidated triaxial specimen, or what we call K0 consolidated simple shear specimens. In this test, liquefaction failure was usually defined as the point at which the initial liquefaction was reached or at which some limiting cyclic shear strain amplitude, which is commonly 5% for dense specimen, is reached. So, you have liquefaction failure. To define the liquefaction failure, and this liquefaction failure is defined, it will be defined the point, which point where initial liquefaction was reached. Now, the issue is this one, sometimes it is difficult to judge whether initial liquefaction is started. For judging that, cyclic strain amplitude, which is normally considered to be 5% for dense specimen, for the and when you reach to the 5% strain, then we say that this liquefaction have started. So, sometime it is based on the strain value or sometime it is based on the pore pressure value. So, that is coming to the continue with the laboratory test. Laboratory test shows that the number of loading cycles which is required to produce liquefaction failure NL decreases with increasing shear stress amplitude and with decreasing density. So, what is here? Suppose if you increase the amplitude of your loading, then it has been observed that liquefaction will occur in less number of cycles. At the same time, if you decrease the density of the sample, soil sample, your loose sample will have liquefaction in less number of cycles compared to dense samples, and those data can be seen in the next cycle figure. While liquefaction failure can occur only in few cycles in loose specimens subjected to large cyclic shear stress, thousands of cycles of low amplitude shear stresses may be required to cause liquefaction failure of dense specimens. So, this has been done here. So, in this case, in this figure, laboratory data is shown from the two tests. Part A is for the loose sample, and which is have a relative density of about 47% dense relative density, and the B is related to the dense end, which have 75% relative density. So, what happens here? This is the number of cycles, and what you could see, there are two ways to judge whether liquefaction is started. The top figure shows the cyclic shear stress with respect to time, second figure is shear strain, and third figure is pore pressure. So, if in the second figure shear strain reaches to a point about 5%, then we can say that liquefaction is started. That is one way. Another way, we say that pore pressure ratio RU should be 1. So, if you see, this is clearly touching the RU here at this point, and this is related to about number of 10 cycles. So, this is about 10 cycles because it go in the 10 cycles. So, in the loose sample, the liquefaction start in the 10 cycles, and here one thing is the loose sample, the loading amplitude is 20 kilopascal. Now, in the dense sample, loading is applied amplitude as a 60 kilopascal, which is 3 times of what has been applied to the loose sample, but still even you are applying the loading 3 times, still liquefaction, the strain is not here. You see, this strain is 5% only, here the scale was up to 20%. So, even reaching 5% is taking so many cycles, it is coming here around 5%. Similarly, if you see the value of Ru, so Ru is not touching to 1, it is barely touching here at the end here. So, that means, and it requires 17 cycles. So, for the dense sample you require more cycles, number 1, at the same time you require higher amplitude of loading compared to the loose samples. So, these are the observations from the laboratory test. Continue with the characterization. The relationship between density, cyclic stress amplitude and number of cycles to liquefaction failure can be expressed graphically from the laboratory data, and that is called cyclic strength curves, and these curves are normally obtained from the cyclic triaxial test. Cyclic triaxial test we have discussed in detail when we talk about dynamic soil properties, and this is shown in the figure in the next cycle. Cyclic strength curves are frequently normalized by the initial effective overburden pressure to produce what is called cyclic stress ratio, and this is called CSR, which we will discuss again in the next lecture in detail. So, here the cyclic stress curves are there. What in these curves? On y axis you have Davidic stress sigma dc, which is in kilopascal here. On x axis you have number of cycles, but this number of cycles is not on the normal scale, rather it is on the logarithmic scale. So, you see 10, 100, 1000, 10,000 or like this. So, here you see that there are 4 curves in this figure, and these 4 curves are for different voids ratio. First one is, top one is for void ratio 0.61 and the bottom is for 0.87. When the void ratio is increasing, that means your sample is getting loose. So, the top sample is the dense sample, while the bottom curve is belong to the loose sample. Now, what we see here, first of all, when the I decrease the Davidic stress, if for let us say if your Davidic stress is more than 120, then for liquefaction you require only 1 or 2 cycles. But as the Davidic stress decreases, when the curve, if it is decreases, so it should be read on the y axis, if I decrease the Davidic stress, then the number of cycles which is required for liquefaction increases tremendously. For example, here it was almost 1 cycle, but if I go here for this amplitude which is 80, you will require 1000 cycles. So, at one place it was 1 and another place 1000, very large difference. Similarly, if suppose for the same Davidic stress, for example, if I draw a line here 60 for the same Davidic stress, here this is loose sample, it is dense sample. So, if I go from loose to dense sample, then the number of cycles for the same Davidic stress is increasing tremendously. So, these data are from the actual data, test data from the laboratory. In the laboratory, the samples has been tested and this has been verified, and that is why this how the hypothesis or theory on the liquefaction has been created. So, continue, this is the last part of this lecture. For the cyclic simple shear test, the CSR, which is called cyclic stress ratio, it is taken as the ratio of the cyclic shear stress to the initial vertical effective stress. So, cyclic shear stress is defined this one, and here what is SS? SS denotes your simple shear test, this stress is generated from the simple shear test. But it has been observed the data which you obtain from cyclic triaxial and then simple shear, they will correlate only when we have some relation. So, cyclic is if I find the same parameter using cyclic or from triaxial test, then it is defined in the triaxial, rather than having cyclic stress we have the Davidic stress sigma dc, and in fact sigma dc q is nothing but sigma dc by 2. So, if I divide sigma dc by 2 by sigma 3c, then you get this ratio cyclic stress triaxial, and it has been observed they are not, if I find the CSR value from triaxial or simple shear, they are not the same, rather than there is a relation. If I get the value from triaxial, then it can be converted into which belong to the simple shear by multiply by a factor, correction factor CR, and this correction factor, the value of this correction factor lies in the range 0.55 to 1.15 and depend on K0 and theory. What is K0? K0 is coefficient of earth pressure at rest, which can be find out using normally like you have 1 minus sin phi or this. So, here what you have different theory Finn et al and then different equation. So, the value of K naught is if equal to 0.4, then we can use this column. If K naught increases, then the CR increases. For example, K naught equal to 1, minimum value of CR is 1. So, the fact this correction factor will be 1, but for most of the soil you will find the K naught in this range. In that case you select the value from this, and or you can use this equation for the CR is given, or this equation can be used if you have the K, just put the value of K naught in this equation and find out, or in another equation. So, this CR can be find out and the CR's the relation can be found. But it has been seen further that in contrast to laboratory cyclic simplest, cyclic triaxial tests are produce shear stress in different directions, which we already discussed. But in the field, rather than having simple shear or the triaxial, you have multi-directional shaking, and it causes pore pressure to increase more rapidly than does unidirectional shaking. So, as a result, if you find the CSR value in the field, then this is about 90% of CSR for the simple shear, and then CSR for simple shear can be done using what we say the CSR for the triaxial. So, ultimately CSR field can be obtained 0.9 times of CSR and CSR triaxial. In the next lecture, that is lecture number 37, we are going to discuss one example using this data, these curves, which will again come on the next lecture, and using this data, and we are going to discuss one example on characterization based on the laboratory test. So, with this I stop it here, this lecture number 36, and thank you very much for your kind attention.